Hello, everyone. Welcome to today's seminar. I am Beth Miyazaki, Senior Scientific Specialist at the Illinois Sustainable Technology Center, which is part of the Perry Research Institute at the University of Illinois. A couple housekeeping items before we get started. I'd like to remind our audience members here to please silence electronic devices as we are recording today's webinar. We will be holding all questions until the end. At that time, I'll bring around this microphone so that everyone online can hear your questions. For those online, you'll remain muted for the entire webinar, but you can type in your questions through the GoToWebinar toolbar at any time, and we'll get to those at the end as well. So with that, I'm very pleased to welcome today's speaker, Tao Xu. Tao is a professor in the Department of Chemistry and Biochemistry at Northern Illinois University. He earned his PhD in chemistry at the University of Alabama. He served in 2 postdoc positions before joining Northern. The first was at Texas A&M University, and the second was in the Materials Science Division at Argonne National Laboratory. His research focuses on design, synthesis, characterization, and applications of novel materials, nanoscale structures, and assemblies for energy and environmental science and technologies, including solar energy conversion, electrical energy storage, chemical catalysts, and gas sensors. He was awarded the NSF Career Award, R&D 100 Award, and earlier this year, the Presidential Research Professorship at Northern Illinois University. So Tao, thank you for joining us. The webinar is yours.
Thank you very much, Beth, and thank you for the invitation. It's my great pleasure to present some of our work in perovskite field. And I thought over my the title of my talk, and eventually I chose this one in order to share as much our experiences with perovskite materials with you as possible. So whenever people talk about solar cells, the efficiency seems to be always the key word. It is true that if you take a look at the growth chart of different PV technologies over the decades, you will find that in general, it takes decades for different PV technology reaches their current state of the art. However, if you take a closer look in this region, let me zoom in this region, and you will find that there's one curve in the thin film single junction solar cell region that started in early 2009 and eventually reached the current state of art that is very compatible with other thin film PV technologies. This is the so-called perovskite solar cells, this line. And because of its high efficiency, it raised a storm of research fever. And as you can see, starting from 2009, the first paper published in this field, after a few years, the efficiency grows so fast, and the number of publications follow the same pattern. And I also added some of my collected data to this chart. You can see that in 2018, it already reached over 1,400 papers. So this is really a research fever that I would address today. And why there's what is the so-called perovskite? The name of perovskite is actually come from the mineral discovered in the Ural Mountain in Russia. And this is the calcium titanates, and its crystal structure is named after the Russian scientist, mineralogist, Lev Perovsky. So this name of perovskite is just a structure of a mineral. And it has a general formula of ABX3 crystal structure, in which the A resides, the A is a chiton, resides on the 8 corners of, for example, a cubic perovskite structure. And the B is the body center atom, while the X is the ions that reside in the center of the 6 faces. So this is the general crystal structure of perovskite. So So what is a hybrid? When we talk about hybrid perovskite solar cells, the word hybrid is really just refer to the some of the inorganic cations, especially the A side, A position cations can be replaced by some organic cations. And this kind of structure can be traced back to 1880s in this paper written in German. I couldn't find this original paper from our library, so I did some Google search. I found out that it contains an organic cation in this perovskite structure. This is the tin-based perovskite structure. And I guess this here contains some strange characters, but I think it's something similar like methyl ammonium type of cations. So it was David Mitchell who spent decades on hybrid perovskite materials, and he synthesized all kinds of hybrid perovskite materials and used them in different areas, such as magnetic optoelectronics. But he just didn't test these materials in photovoltaics, so unfortunately he didn't hit the big time. And I had the chance to ask him why you didn't try those materials on photovoltaics. He told me that because he works at IBM, the companies have specific targets, so he couldn't work on this photovoltaic field. But he has a very nice review paper published on Chemical Review in 2016. I would suggest that you can read these review papers that contains a lot of stories behind it. So what is the perovskite in perovskite solar cell? What is exactly material? One of the champion material is this methyl ammonium lead trihalide material, or in short, we can put it as MAPBI3. So this is the widely used hybrid perovskite material in perovskite solar cells, with the cation part A position replaced by the methyl ammonium cation. So the synthesis of this material is also quite simple. You just have lead-2 iodide react with methyl ammonium iodide to produce this MAPBI3. The first report on the use of this MAPBI3 as part of a solar cell was in 2009 by Miyazaki's group in Japan. And in this work, he actually used this MAPBI3 as a dye-sensitizer in dye-sensitized solar cells, in which this MAPBI3 material is used as just a solar absorber rather than electron transport or hole transport materials. And the cell is still the classic liquid phase dye-sensitized solar cells, the so-called Gratzel cells. And the reason why he used this material is that because this material can cover or absorb the light all the way to 800 nanometers. So he, with the hope to expand or increase the efficiency of the solar spectrum. However, the efficiency is only 3.8%. So after the publication of this first paper on JAX, it didn't receive too much attention until in 2012, Henry Smith's group at Oxford, they presented their work on the first solid-state hybrid perovskite solar cells using this MAPBI3 as the solar absorber, as well as the whole transport layer and the electron transport layer, as indicated here in this picture. So the efficiency reached over 10% because of its solid, and it only used this solution-based processing method to fabricate the device. So many other groups come into this field and start to research this fascinating material, photovoltaic material. So the process of making such a film is quite simple. You just dissolve lead iodide and methylammonium iodide in certain organic solvents such as gamma-butyrolactone or NMP or DMSO or DMF. So you get this yellow greenish solution, and then you just job case it, for example, by spin coater. After the solvent quickly evaporates, you can get this dark brown thin film. This is the so-called perovskite thin film. But of course, nowadays there are lots of other type of thin film technology that can coat much better perovskite films, such as this blade technology. Because the spin coating doesn't give you a very uniform distribution or uniform film along the radial direction. So I noticed that in the history of perovskite solar cells, there are something quite intriguing. So Henry Smith submitted his paper, the first paper in solid state perovskite solar cells, in the May of 2012, and he got his paper published in September of 2012. Meanwhile, at the other group from Michael Grattel's group, and also another work from Michael Grattel's group and Nanju Park's group, they also submitted a similar work in July of 2012, but this paper got accepted earlier. So there's quite interesting coincidence. So later I find that there's a interview published by Nature, and it says that Smith did his postdoc research with Grattel and says that they are still very friendly, but there are certain computation there. So indeed, the field of perovskite solar cells is highly competitive. So because people think this is a very old type of materials, but now it becomes very popular and it's very attractive to the field of photovoltaics. So they call this is a renaissance of hybrid perovskite. So if it's a renaissance, my question is, who is Shakespeare? It's Henry Smith or Grattel? Maybe everyone has their own opinion. So this is an open question. So after Henry's work, there are lots of groups jumped into this field, especially these OPV people, because they know how to make good films. So quickly, the efficiency of perovskite solar cells were pushed to over 20%, nearly 20%. For example, the work reported by Yang Yang's group at UCLA, and they used this thin film perovskite layer as both the light harvesting layer and the charge transport layer. And they reached the efficiency over nearly 20%. But the trick here is that you have to make a very smooth film with a large domain size in the film. And another trick is that you have to use, for most of the champion cells, you have to use gold as the counter electrode or the cathode. The reason why so far the champion cells all use gold as the electrode is will have to be tracked back to the band structure or the energy diagrams of this MAPBI3, the classical hybrid perovskite material. Its valence band resides at about 5.43 electron volts between below the vacuum level. So when the incident photon strikes on the material, it generates the electron and holes, right? And for the purpose of photovoltaics, we want the electron to go to the anode side, which is the transparent FTO electrode. That is to say, we have to block the electron transfer, electron transport to the other side. So we have to have some blocking, electron blocking layer. And this layer the materials suitable for this layer is this spiral MEOTAD. This is the organic based electron blocking layer, or the so-called hole transport layer. It has a lumen way above the conduction band minimum of MAPBI3, but with a HOMO orbital between the VBM and the electrode, which is gold here. I will later explain why we have to use gold. And then once the electrons transport to the FTO, you don't want the electron to go back to the holes in the valence band maximum of the MAPBI3, right? So you have to have something called electron transport layer, or the so-called hole blocking layer here to block the back electron transfer. And this material can, the suitable material is titanium oxide, because its valence band is deep here, so that the electron can not go back, easily go back to the valence band of the MAPBI3. And its conduction band minimum is between the Fermi level of FTO and the conduction band minimum of MAPBI3. So this is the reason why we use TiO2 as the electron transport layer here. So as the electron goes through the device and reaches the counter electrode side, which is the cathode side, you want to have the electron to refill the holes in the valence band of the MAPBI3. However, think about the electrical power is the product of currents and voltage. So you want both high currents and high voltage. Here, if you have the electron is provided from a counter electrode with a less work function, or here, for example, then the energy gap between here and here are all wasted, because this is the potential energy between the counter electrode and the VBM. The electron transports through the higher level of the electrode and the lower level of the valence band of MAPBI3 will have to be converted to heat. So you don't want a lot of electron potential energy to be converted to heat. So you want this Fermi level of the metal to be as close to the VBM of the MAPBI3. That's why, because of the value of this VBM of MAPBI3, you have to find some large work function metals. And of course, the intuitive selection would be for large work function metals would be precious metals. Yes, it's true that gold has a pretty high work function. But once you carefully read this work function chart, you will find that some other metals, such as nickel, also has a fairly high work function. So since gold, the choice of gold as the cathode would be a very costly choice, right? So especially gold price is around $1,500 per ounce. So if you take this price and calculate every 1 gigawatt of perovskite solar cells will have to use 7.8 tons of gold, assuming that the conversion efficiency of perovskite module would reach 20%. And we only need 80 nanometers thick of gold electrode. And every year there are about 100 gigawatt solar panels installed globally, this will need approximately 780 tons of gold per year, which is not sustainable because the annual consumption of gold on industry purpose is only 300 tons. The others just for the financial purpose or jewelry purpose. So this is using gold is certainly not a sustainable option for the commercialization of perovskite solar cells. This prompts us to think some other choice. So we use nickel as the counter electrode. Nickel has the very similar work function as gold, but at much lower price. So we actually have used this nickel as the counter electrode and conducted some research. And here is now a nickel-based perovskite, the performance of our nickel-based perovskite solar cells, which we published in 2014. At that time, the champion cell is around 14% when we get this work published, and quickly it was the efficiency was the record was broken by Yang group. So we use a different anode material, which is this titanium oxide nanowires, single crystal nanowires. But this is not the most important part. The important part is that when we compare the same type of cells we made, when we use gold and use 300 nanometer nickel, we find they are fairly competitive. That means that if we properly coat nickel onto the perovskite and whole transport layer, we should get competitive results or efficiency, the same or at least the competitive result as the gold-based perovskite solar cells. And you also notice that for nickel, you have to coat a much thicker layer because nickel has a relatively lower conductivity than gold. So if you coat less than 300 nanometers, you will suffer. The cell will suffer from high serial resistance, so low fill factor. And this work actually attracted some attention from financial field. So Yahoo Finance reported on our work, quite surprisingly. Maybe the Wall Street people always try to sell nickel at the price of gold. Okay, so the next thought we had over perovskite solar cells was its instability, especially due to moisture. And this is the video clip I got from YouTube. As you can see that within 30 minutes, the perovskite layer will suffer from degradation by moisture. And this is the fluorescence image of this perovskite thin film. And after 30 minutes, they actually just become the classic, the characteristic yellow color of lead iodide. And the reason behind this degradation process is due to the methyl ammonium, which is highly water soluble. So the water can easily hydrolyze it because it carries a net positive charge. So once the positive charge, when the positive charge, the methyl ammonium is washed out by water, then the remaining negative charge, the inorganic framework collapse. So this is the general reason why this material is so vulnerable to water. So As chemists, we know that if we want to enhance the electrostatic interaction between the ionic compound, we can reduce the radius of these ions. For example, we can change from iodide to bromide or even chloride. However, when you change the ions, these halides, you will find that their absorption of the color apparently undergoes drastic change, and it loses the brown reddish color. So also as a chemist, we know that we have some other type of halide. It's a so-called pseudo halide. So this is our second approach, try to improve the stability of perovskite film. So we use pseudo halide such as thiocyanide as the precursor, and to produce the thiocyanide-based perovskite thin film. And it's quite astonishing that we found that for the regular MAPBI3 thin film, it only lasts actually half an hour in 95% humidity air, or in a regular lab air, it just takes a few days to turn to this yellowish film. And this is the reflection spectrum of the films at different time. And however, this thiocyanide-based, pseudo-halide-based perovskite seems quite stable under humid air. And as you can see that even after 4 hours in 95% humidity, the color still remains black in the center, and some part of it becomes white. But if after 30 days in lab, it still remains black. So this is quite exciting. However, when we measure the efficiency, it seems that this pseudo-halide-based perovskite is not very competitive to the conventional MAPBI3-based perovskite solar cells. And this work is done in our lab. So at that time, our lab has the capability of making MAPBI3 the conventional MAPBI3-based perovskite at the efficiency of about 12%. There's a German group led by Dr. Heilig. He saw our paper on angewandte Chemie, and he quickly made the single crystals of this pseudo-halide-based perovskite solar cells, perovskite material. And he realized or discovered that this material is actually a two-dimensional material, and it's very similar to the Rudolphin-Popper type of perovskite material. And so we can use his crystal structure of this pseudo-halide-based perovskite to explain why water it becomes more water tolerant. So the pseudo-halide SCN attached to this lead with the dangling atom of nitrogen here. And the nitrogen can form strong hydrogen bond with incoming water molecules. And because the opening here is just a few water molecules, so when this water molecule binds to the terminal hydrogen molecules, it actually blocks the entrance of the additional water ingression. So this is a potential explanation of why this pseudo-halide-based perovskite thin film is exhibited improved water stability or moisture stability. And we further expanded this idea to some other ions by doping divalent ions, such as selenium cyanide. So we use lead cyanide as the precursor and doped approximately 10 weight% of lead cyanide in the precursory solution of MaPbI3. And we found this thin film exhibits much better water tolerance with respect to the conventional MaPbI3. Within 70 hours, the % relative humidity at 40 degrees C and under lab illumination, we see just a tiny bit of change of its reflectance spectrum. And we think there's a interaction between the cyanide in the organic framework and in the inorganic framework and the organic ketones through this pseudo-hydrogen bond interaction. So we conducted some infrared spectroscopic study and find out that in infrared, the NH bending and the stretching all undergo a blue shift, which indicates that there's a interaction between the hydrogen and something else, some additional species, which is the cyanide, the ions. And this helped the attachment of the organic ketones with the inorganic framework and help this film to tolerate the water hydrolyzation of water. And we also tested the efficiency of this lead cyanide doped perovskite film of perovskite solar cells, and we found that they are relatively more stable than their counterparts, which is MaPbI3 based solar cells without any packaging. However, the efficiency of our cells dropped significantly from 17% to about 10%. So we learned a lesson here. And recently, we found that a recent work by Jinsong Huang's group, they actually just used this lead sulfate as the top layer to cover the perovskite layer, so that this layer can prevent the water, because the lead sulfate as lead cyanide or exhibit good good water resistance. So their efficiency can still remain 20%. Another bonus that we got by doping this divalent ion, such as cyanide, is that it is known that the iodine in the perovskite layer can actually migrate, especially when the silver is used as the counter electrode, because considering the high cost of gold, many groups now start to use silver as a counter electrode. But the migration of iodide through this whole transport layer will cause the reaction between iodine and the silver and form silver iodide. As you can see that this silver electrode-based perovskite always suffer from the formation of silver iodide after just 1 week. You can see at the edge of this electrode, you can see this dark layer. This is silver iodide, and we actually identified the nature of this iodide with XPS. As you can see that when we scan this part, we see a strong signal of iodine. However, when we have this lead cyanide doped perovskite layer, after 2 weeks, we don't see any signs of silver iodide on the edge of the electrodes. And we actually also scan it, and we don't see any strong signal of iodine on the top of the electrode. So the two cells are made side by side in the same process. So this is something that's worth to study further. So it is clear that chemical doping can help the chemical stability of perovskite layers. So our next thought was to study some enhance our fundamental understanding of this fascinating material. Just think about it, why this material has such a long carrier lifetime. Because the valence band of this perovskite material resides mainly on the inorganic framework that contributes mainly from the valence band of iodine 5p orbital. And its conduction band also resides in the inorganic framework that is contributed mainly from the lead 6p orbital. So both the conduction band and the valence band are in the same material. Why this material has such a long carrier lifetime and long diffusion length? Meanwhile, what are the roles of these organic cations? So these are our puzzling questions. So we want to study this, especially this role of rotors, the role of these cations. So in order to study these roles of the cations, let us first think about these cations. So these cations are organic cations, and they have very polar geometry. Most of the positive charge are distributed on the 3 hydrogen attached to the nitrogen, because nitrogen has higher electronegativity than hydrogen, right? And this is an unsymmetrical cation. And a very interesting paper, this JPCL paper, showed some experimental evidence that this cation always in constant rotation mode. One along the CN axis, and the other one is actually out of plane rotation. So because this is an unsymmetric charge, so the rotation of these cations will significantly change the local electric field. And if there's a photo-induced charge generated, then this charge will have to subject to the local electric field change generated by the rotation of this, we call it rotors. So there are certain kind of electron-rotor interaction here. And so in order to study this effect, we actually borrowed the idea from physics in the field of superconductivity. People always use this isotope effect to study the electron lattice interaction. Now here the lattice include these rotors, and this is why perovskite material is very special, because most of the solid materials only has a vibration mode, but this material has rotation mode in it. This solid material has a rotation mode in it. So we made 4 different isotoped MAPBI3, with the first one all hydrogen based, and the third one we have the nitrogen hydrogen deuterated. The third one we have carbon hydrogen deuterated. And the purpose for these two is to find out whether the vibration mode between the vibration mode of hydrogen on nitrogen or on carbon would affect the carrier lifetime. And the fourth one is the fully deuterated perovskite, MAPBI3. So with these 4, we can get a further study onto the nature of this electron-rotor interaction. So we made, in order to have a fair comparison, we made single crystals of the 4 different type of isotoped MAPBI3. And we carefully examined their crystallinity, and we first cleaved the single crystal and checked the cleaved surface, and we found they are very smooth. There's no cracks on it, so it makes us very comfortable. And also we carefully examined all the intermediates that we use to synthesize this 4 different isotoped MAPBI3, and these are their NMR and mass spectroscopy, and we found that they are exactly what we expected. So now we are confident that we can compare these single crystals in terms of their optoelectronic properties. And also we conducted this synchrotron high resolution XRD of all the 4 single crystals, so that we found that these single crystals are all comparable with each other. So whatever we studied based on those single crystals should represent the effect of these isotopes. So we measured the time resolved photoluminescence, and we find out that the pure hydrogen-based perovskite has the longest single crystals has the longest carrier lifetime, while the 2 half deuterated MAPBI3, so one is the nitrogen hydrogen deuterated, one is carbon hydrogen deuterated, both of them shows comparable carrier lifetime. However, when we tested this fully deuterated MAPBI3, its carrier lifetime drops significantly. So the carrier lifetime seems to have a direct link with the mass of these rotors, these titanic rotors. And so we carefully study this trend and find out that the trend is actually in line with the vibrational rotational frequency of the 4 rotors. So we can use some fundamental, just very classical quantum mechanics to calculate to actually arrange, to order this frequency of these rotors based on their momentum. Our theoretical collaborators also provided some DFT calculations, and they find out that when the rotors align in different directions with respect to the crystal faces, and they found that the polaron trapping energy changes significantly. For example, when the rotors are aligned or aligned along the 100 plane, then the electron trapping energy is much different when you change the orientation of the rotors to 110 direction. So this indicates that there's some interaction between these rotors and the photo-induced charges. But this is not a single rotor and a single charge interaction. It involves all the rotors nearby the photo-induced charge. So it forms this so-called polaron interaction. And we also noticed another paper published by Podozorov and Xiaoyang Zhu's group, and they also discovered this polaron interaction from this from the nearby charges with the photo-induced charges, and this is also a polaron interaction. Okay, so we further deepened our fundamental thoughts on this fascinating hybrid perovskite materials. Many people may like to use high temperature or low temperature or high magnetic field to torch this material. And here we choose a different approach. As chemists, we like to alter the bond length and bond angle to see if the property of the material changes. So we use high pressure to modulate the crystal structure of this hybrid perovskite material. And this is conducted by a pair of this diamond envy. And then it allows the in situ study of the structure by X-ray or photoluminescence spectroscopy. So we made these single crystals of MaPbI3 perovskite material, and at 1 atm we found that its phase is I4 MCM, but at increased pressure up to 0.4 gigapascal, it undergoes a phase change to IMM2, and at the same time, so we can measure the we can actually also measure their different optical properties, such as the band gap, using the UV-Vis spectrum, and we find out these red lights are experimental data. We find out that as the pressure increases from 1 atmosphere to 0.4 atmosphere, the band gap actually decreased. But all of a sudden, when phase change occurred, then the band gap increased again. Now, our theoretical calculation indicates that if there's no phase change, then the band gap of this MaPbI3 single crystal would continue to decrease. So it indicates that if we can keep the phase without phase transition, then the band gap can continue to decrease. And the reason why this MaPbI3 encounter this phase diagram, phase change, is because it's the lead and the iodide bond is not perfectly linear. It's about 172 degrees. So there's a kink in this band, in this bond. And so when the pressure increases, this band folded and causing the phase change. And because of this shrinking of the lattice constant, some shallow defects becomes, some deeper defects, originally deeper defects, becomes shallow. And so we also noticed that the carrier lifetime before the phase transition increased. But after phase transition, carrier lifetime continues to decrease. So this carrier lifetime change also follows the phase transition. And this is actually an interesting phenomenon because the value of the valence band may increase by compression to make this deeper defects become shallow defects. But the elevation of the valence band actually help to allow some metals with low work function to be comparable with the valence band of the MAPBI3. See, if we can somehow increase or levelate the valence band of MAPBI3, then we can use some other metals with less work function. So this is some meaningful role or meaningful effect of this valence band elevation. And as I said, that because there's a kink in lead iodide bond in MAPBI3 that caused the phase transition at relatively low pressure, right, 0.4 gigapar. So we choose another perovskite, which used the formylmethylene as the chiton, and this material has a relatively straight lead iodide bond, and so we can compress it all the way to 7 gigapar without phase transition. And during this process, we find that the lattice constants continues to decrease. However, the band gap actually decrease all the way to reach the Schottky Queisser limit. We know that single junction solar cells, the efficiency of single junction solar cells is limited by the so-called Schottky Queisser limit. So there's some optimized band gap, which is about 1.38 electron volts. So by compression, we can actually push down the band gap of FAPBI3 all the way to this optimized Schottky Queisser band gap. And meanwhile, we also notice the carrier lifetime increase during this compression. And very interestingly, when we remove the pressure, so decompression, we found that the band gap narrowing does not come back to the original value completely. There's still some remaining band gap narrowing effect. So this is the band gap before compression, and this is the band gap at 1 atmosphere, but after decompression. You see that there's a gap between them, so there's some ambient retainability of this band gap narrowing by compression. So this work was highlighted as perovskite under pressure by Science News, or Advanced Science News. So now our first thought is that can we expand the application of perovskite, hybrid perovskite materials beyond the photovoltaic? And if we take a broader view in this field, we found that many work are done in the field of photovoltaics using hybrid perovskite. Some work was also conducted in the X-ray and the gamma ray field, gamma ray spectrum. using perovskite materials as gamma ray and X-ray detector for medical imaging, because this lead-based perovskite is very sensitive to gamma ray and X-ray, and it can generate gamma ray or X-ray generated induced photoelectrons, which give you much better imaging resolution, because we can people can synthesize very tiny perovskite crystals. And in IR field of the electromagnetic spectrum, people also used applied perovskite materials as IR LED or IR detectors. But there's a region that is omitted so far by the field, which is the UV and extreme UV region. So this region has a lot of important applications, such as extreme UV lithography. And this region, the photon wavelength in EUV is about 10 to 20 nanometers. In addition, in the UV region, there's another important technology. It's called non-line of sight UV communication. The idea is that to use UV light as the information carrier for short range cyber-secured communication. As we know that UV light has a very short wavelength, so that the behavior is more like particles, so they can scatter in the air. In the lower level of air, there is no UV light below 280 nanometers, because most of this high energy UV photons has already been absorbed or scattered by the upper level atmosphere. So at the lower level atmosphere, there's no such UV photons. So when you generate such UV photons by a transmitter, it won't be affected or interferenced by other UV photons at the same frequency from the solar light. But you need a sensitive receiver to receive this scattered UV light. So, and the propagation range is typically just a few thousand meters. So this can secure the information within just the desired range. So we use this FAPB-Cl3 based perovskite nanowires as the UV absorber. Because we found that they have very good absorption in the UV region, especially this deep UV region. And as you can see from this this reflectance measurement of a thin film of FAPB-Cl3 nanoparticles film. And by adding lithium chloride into the precursory solution of formamidinium lead triiodide, lead trichloride solution, we can actually improve the crystallinity of the resulting nanoparticle, nanowires or nanorods. So here are the X-ray diffraction spectrum of the lead chloride, lithium chloride, and the FAPB-Cl3 thin film and lithium chloride doped FAPB-Cl3 thin films. This all indicates that we get much better crystallinity with the lithium chloride doped formamidinium lead trichloride. So we made this thin film into this optoelectronic structure, and we measured their response to different UV wavelengths for 360 nanometer UV, we found that it's quite powered by AC voltage, and we found that the signal, the photoelectric signal is also oscillating at the same frequency as the AC power. However, when we change the UV wavelength to 250 nanometer, we found that the intensity of the photoelectric current oscillating across the baseline. This is very strange because the intensity of light changes. That's cause the oscillation of your photoelectron. But the phase of the there's no phase of the intensity of the light. So why the photocurrent would decrease below the baseline? So this puzzled us. And meanwhile, we also tested silicon-based photo detectors, photodiodes. They don't show this behavior. And so we think that because the FAPBCl3-based perovskite has very good absorption in deep UV region. So when you have long wavelength UV, they only goes to the conduction band, the hot state here, and then they inject it into the FTO side. But when you have a high energy UV photons, they excite the photoelectrons to a very high level of the hot states in the perovskite material. And at this state, the electrons can go either way. So that causes the cancellation of the currents and cause the current to go below the baseline. So this is highlighted, this work was highlighted as the back cover page by JMCA. And lastly, I would like to talk about the toxicity of lead in perovskite. So there are recent Nature comments on the toxicity of lead in perovskite materials, especially these champion cells. They all use lead. But even people start to think about tin-based perovskite, but unfortunately, tin has similar toxicity problems as lead, maybe even worse. So this has to be considered before the commercialization of perovskite solar cells. Especially, people think that perovskite solar cells, the best application for perovskite solar cells is in building integrated photovoltaics. And so I did some calculation, and we find out that the lead content per unit area in PSC is 100 times greater than the government regulation. And the PV, since PV technology naturally require widespreading area, so this has to be taken into consideration. We hope that in very near future we can present our work on the to tackle the toxicity of lead in perovskite solar cells. So with that, I would like to summarize my talk, especially the lesson we learned. The efficiency is not the only topic in perovskite materials and or perovskite-based solar cells. The back contact metal electrode is a bottleneck, and the vacuum coating is not a acceptable choice for industry to commercialize this technology because it will significantly slow down the production line. And the chemical stability of perovskite materials can be improved by ionic dopants. But the lesson we learned is that the location is very important. You have to find the right location. Right now, we believe that the cap layer is the best location for this such doping, and in order to balance the efficiency and the stability. And there are a lot of fundamental science that can be explored in perovskite materials. We believe that lead is still an issue before commercialization. And there are more than just the PV applications for this fascinating hybrid perovskite materials. And with that, I would thank you, my students who did all this work, and my collaborators at NREL and Carnegie Institute of Washington, as well as at Argonne. And thank you very much for your attention.
Thank you. Wonderful presentation. We will be taking questions now. Our online audience, I'll remind you that you can type in your questions through the GoToWebinar toolbar. I will be taking one question from online right now, and then we'll get to the room next. So John from online says, thank you for addressing the lead issue. Is tin the only alternative?
Tin is not the only alternative. If we take a look at this periodic table, that there are people that work on group 3 and group 5 metals. But remember, all these metals are heavy metals. Here, all these metals are heavy metals. If you don't use lead, you use bismuth, or these are all heavy metals. And this one, sodium, is even more toxic than lead. So if you go above tin, the bivalent tin ions is fairly toxic, because both tin 2+ and lead 2+ can cheat our body system, and our body system will treat them as calcium 2+. So perhaps germanium would be a choice, but it's not very stable. It's even worse than, the stability is even worse than tin-based perovskite materials. So there are a lot of challenges. But hopefully in the near future, we will present some work on the lead issue. So I will keep everyone updated.
Thank you. A couple questions from the room.
Okay.
Thank you for the talk. I really appreciate it. It was very interesting. And I actually did work this past summer at NREL with the Perovskite group there. So.
Oh, great.
My question was, what are your comments on? You made comments on the metal cathode and different absorber layers. But what are your comments on for stability related concerns on the whole transport layer? And sort of, most groups have just sort of used Spiro as the default transport layer, but recently there's been some new developments in that. And do you think that that could sort of solve the, or at least several of the degradation mechanism issues?
Yeah, that's a great question, and I appreciate that. And actually, this whole transport layer contains spiral, right? And it's not just the spiral; it also contains a very lithium salt that is extremely sensitive to moisture. You have to combine these two together as to case into the whole transport layer. So some inorganic whole transport layer should be the way to go. Especially, I mentioned that the metal electrode has to be vacuum coated onto these vulnerable organic layers, especially for nickel, because we cannot evaporate nickel. We have to use sputter. So during sputter, the high energy ions will strike on the soft or vulnerable organic layers and damage the organic layers. So this is why it's very challenging for us to coat nickel onto these organic layers without damaging them. With the help of inorganic whole transport layers, such as nickel oxide, then this problem may be solved. Also, I want to emphasize that if in the future we can invent this paste-based metal electrode fabrication process, so just like a silver paste that is widely used in silicon-based solar cells, then because this paste contains a certain solvent, and on top of perovskite layer, on top of this perovskite layer, we will have to spread the solvent-containing paste, metal paste, and this solvent are typically either polar solvent or non-polar solvent. Polar solvent will dissolve the perovskite layer. Non-polar solvent will dissolve the organic whole transport material. So there's simply just no way out to avoid this problem when we have this organic whole transport layer. So in the future, if we can have inorganic whole transport layer that function exactly or even better than the organic-based whole transport layer, that will be a major breakthrough in the field. Did I answer your question?
Yeah, that was really great. Thank you. I had a quick follow-up. You mentioned the deposition method for the cathode or the electrode. I was just curious on what are your thoughts on doing sort of like more of a roll-to-roll style of printing versus what Professor Snaith is doing at Oxford PV, more of like a vapor deposited technique.
You mean the electrode, right?
Yeah, the electrode, yeah.
Yeah, just like I said, if we want to pursue roll-to-roll deposition of the metal electrode or the counter electrode, then we have to invent the paste-based electrode rather than this vacuum coating. So it uses paste to spread onto the perovskite film, or just use the roll to roll over onto the perovskite film. Then that will achieve mass production. So currently, the vacuum-based deposition wouldn't fly, in my opinion.
Okay, thank you.
Yeah.
Before we get to the next question, I'm going to announce the final call for questions online, so you can get those typed in before we finish the webinar in the next few minutes. So we have a question from Rosemary online. She asks, do you know if this research is being applied to the decommissioning of solar panels as they near the end of life stage? And is there any research going forward to safely recycle these panels?
Oh, okay, that's also a great question. I actually forgot to cover this type of question in my talk. So as we know that the hybrid perovskite materials are very vulnerable to water. Water can just easily dissolve them. So this is a bad thing for the stability of the for the devices, but maybe in some sense a good thing for the recyclability, because you can easily wash out all these contents of inside the device, of course, except this sintered TiO2 layer. So in the future, if we can have inorganic whole transport layer, then everything will be insoluble by water, except the perovskite layer, so that we can easily wash off the devices after the end of their lifetime. And we recollect the perovskite materials just by water, and then we can, if there's no contaminants goes into this layer, then we can just use this. We can just desiccate the water and use the remaining solids as the precursor again by dissolving it in some combined solvents, right? We can just directly use them. This will be the most convenient way or most cost-effective way to recycle the perovskite materials at the end of their lifetime. That's my opinion. Did I answer the question?
Thank you. There weren't any more questions that came in. Rosemary says, yes, you did answer her question.
Oh, great.
There weren't any more questions that came in, so we'll end the webinar. Are there any, what final thoughts would you like to leave us with?
Yeah. I think this is a exciting field, and many different applications are now proposed or implemented based on the perovskite materials. So, like I said in the beginning of my talk, efficiency doesn't have to be the only keyword in this field, and we should pursue some other directions, especially for efficiency. You have to have a very man-powered team to reach very high efficiency. Currently, the efficiency is already over 24%. So it requires a lot of teamwork to reach that high. However, there are many other fields that may be suitable for perovskite. For example, I see people that use perovskite materials for quantum information science because they can dope different kind of transition metals in it and study the spin orbital coupling effect in the perovskite material, because this material can easily form a very nice single crystal. And so I just try to throw my thoughts, but I would like to encourage people to think more ideas to enhance the viability of this material. And yeah, that's my last thought.
Wonderful, thank you. Tao's slides and presentation will be available online next week, and I can send an email out when that's available. So, Tao, thank you.
Feel free to contact me if you have further questions.
Sounds great.
Okay, thank you.
Yep, bye-bye.